All right, so the work done when the gas expands by that much is that much, and if you sum over all the work, the integral is the total area under the curve. So when the gas went from this state to that final state, that was the work done by the expanding gas, okay? In this case, that was the work done, okay? So what I want you to notice is the following. Okay, so in these diagrams, all the initial points are the same and the final points are the same. But the work done is different depending on the path taken, okay? So the work done by a gas is path dependent, okay? All right, so I want to make sure that you understand two things. A PV diagram is a very useful tool when you're working with gases. You can describe different processes by showing trajectories on a PV diagram, okay? And the work done by the gas is the area under the curve. So the area is equal to work done by the gas. And the work done is path dependent, okay? Did you guys understand all of that? Okay. All right, any questions on that? Okay. All right, so a system can be taken from an initial to a final state in an infinite number of ways. The work done and heat exchange are path dependent. Okay, so when you add heat to the system, when you're taking it through a given process, you might be adding heat and whatnot. The work done and the heat added are path dependent. So, however, the change in internal energy of the system is path independent. Okay, so we'll come to that. Okay, so now here's the first law of thermodynamics. The first law of thermodynamics states the change in internal energy is the heat added to the system minus the work done by the system. Okay, this is path dependent, path dependent. This is path, so path dependent, path independent. Okay, so if you take a system from this initial point to that final point, okay, the amount of heat added and the work done depends on the path, but the difference in the two is path independent. Okay, so the internal energy is just a function of state, okay, and it doesn't matter how you got from here to there. The change in internal energy, this depends only on the final state and this depends only on the initial state, okay? It doesn't matter how you got there. So the change in internal energy is path independent, okay? All right, so here's our thermodynamic system and here's the sign convention that you'll see. Okay, so I just want you to be aware, some people write some textbooks, you'll be doing a thermodynamics course. Some people write the first law of thermodynamics like that, okay? So that's their sign convention. In our sign convention, where we are writing the first law of thermodynamics like this, we take everything from the perspective of the system, okay? Q is positive when the system absorbs heat, okay? So when you add heat to the system, Q is positive. When you remove heat from the system, Q is negative. Okay? W is positive when the system does work. So when the system expands and it does work, W is positive. So when you compress the system, you do work on the system. Okay? The system does negative work. Delta E is positive when the internal energy of the system increases. Okay? So that's the sign convention we use. Okay. Did you guys understand that? Any questions on that? Okay. Samuel? Good? All right. So here's a PV diagram. Okay. Any curve you draw is a process on that PV diagram. Okay. So how many different processes can you have? Hmm? Yep, you can have an infinite number of processes. Okay. These blue lines, these are special processes. These are called isotherms. What is an isotherm? Okay, so iso means constant, therms means temperature. Okay, so if you are using an ideal gas system, if you hold the temperature constant in this process, uh, so P N R T over B. Okay, what is this graph? Y equal to 1 over x, or constant over x. That's a hyperbola. Okay, so these are isotherms. Okay, so these are constant temperature processes. Okay, so you want to be familiar with these processes. Isovolumetric process, you're keeping volume constant. Okay, so those processes, A is an isovolumetric process. Okay, so in this process, how much work is done? What was the work done? The work done was the area under the curve. So on a vertical line, there's no area, so no work is done. Okay. Did you guys understand that? Okay. Isobaric process, constant pressure process. Which one of these curves is a isobaric process? D. Okay. Okay. So the work done in this would be that area underneath that curve. Okay. Isothermal process, constant temperature process, all the blue lines are isothermal process. And these are higher and higher temperatures, okay? So the temperature is increasing that way. Adiabatic process, no heat is exchanged with the surroundings, okay? So these are 4 special processes that you need to remember, okay? And now what we'll do is, so what is the first law of thermodynamics? Delta E equal to Q minus W, okay? So we'll say something about one of these terms for each of those processes, okay? Now E, what is E? Internal energy, okay? So for instance, the internal energy of this gas depends just on the state of the gas. It doesn't matter how you brought the gas to this state. Okay, so the internal energy is a state function. Okay. All right, so here is what is called a cyclic process. Let's take the gas. So again, we are doing a PV diagram. Let's take the gas from this initial state and we'll go along this path. Okay, and again, and then come back to this state. What is the change in internal energy? 0. Okay, the initial and final state are the same. So EF will equal EI. So change in internal energy is 0. Okay. So now we have said something about this term. Okay. So for a cyclic process, change in internal energy is 0. If the system did any work, that's how much heat you must have added in that cyclic process. Okay. Okay. So that's what that is. An isothermal process. Okay, what's an isothermal process? Constant temperature. Okay. So here is the formula for internal energy for an ideal gas. So we'll talk about an ideal gas. N is the number of particles, and the kinetic. So let's say it's an ideal monoatomic gas. Okay, and so the internal energy is N times for a ideal monoatomic gas, it's just the kinetic energy, and kinetic energy for a monoatomic gas is 3/2 kT. So the internal energy just depends on temperature. Okay, so in an isothermal process, what is an isothermal process? Constant temperature. What does that mean? Internal energy is constant. So for an ideal gas in an isothermal process, the internal energy is not changing. Okay? So if this were an ideal gas system, and this is an ideal gas system, along this point, the internal energy is the same. Okay? So temperature and E are constant along these curves. Okay? All right, so what does that mean? Q minus W. If this is 0, if any work is done, the amount of heat absorbed is the same. Okay? So for an isothermal process and a cyclic process, this is true. Okay? These statements are true. An adiabatic process is a process where no heat is absorbed. Okay, so delta E equal to Q minus W. Okay, so no heat is absorbed. So if you did any work, that means your internal energy decreased by that much. Okay. Now, so here's a useful analogy, a financial analogy. You can think of this as your earnings, this as your spending, and this as your bank balance. So in an adiabatic process, you didn't earn anything, and if you spent any money, your bank balance decreased by that amount. Okay. All right. So here is an isothermal process. Okay, what is an isothermal process? Constant temperature process. Okay, so if this were the initial state, that were the final state, when the gas expanded, it did work. How much work did it do? The area under that curve. Okay, so this is the work it did. Now for an isothermal process, for an ideal gas, it's easy to calculate this area, and that's what this calculation is. So the work done is the area under that curve. So you have to know P as a function of V. Okay, but we know that for an ideal gas, P as a function of V is that for an ideal gas. Okay? And this integral is easy to do. That's log V. Okay. So for an ideal gas, if that's the final volume and there's the initial volume, that's the amount of work done when the gas goes from this initial volume to that volume. Okay. And if the gas was at a higher temperature, the curve would be somewhere there, you know, and the work done, see, the area would be, the work done would be higher, okay? So if the temperature were higher, the work done would be higher, okay? What is an isobaric process? Constant pressure. This is a constant pressure process, okay? And here is another constant pressure process, okay? All right, so the work done during, in an isobaric process is the constant pressure times the change in volume, okay? So if the gas expands, you do positive work. If the gas compresses, the gas has done negative work, okay? If VF is greater than V initial, then you've done positive, the gas has done positive work. And if V final is smaller than V initial, the gas has done negative work. Okay. Isovolumetric process. This is also sometimes called an isochoric process. Okay. And that is, these two processes are isovolumetric process. And the work done is 0. The area under those curves is 0. Okay, so the work done is 0. Okay. So delta E equal to Q minus W. So if you absorb any heat, all of that goes into increasing the internal energy. Okay, so if you're earning stuff and you're not spending any, your bank balance is increasing. Okay. You guys understanding this? All right, think about this one before you answer. Okay. What is this? An isotherm. That's an isotherm. This is lower temperature than that. Okay, so when you go from this curve to that curve, okay, so remember isotherms are also, so this is internal energy and that's internal energy. Okay, so the temperature is higher, this internal energy is higher than that. Okay, do you guys understand that? Okay. Okay, what we're going to do is we're going to heat the gas, and there's the initial state, and we're going to heat the gas from this initial temperature to that final temperature. The temperature is the same along there, so I'm going to go from here to there, or I can go to that higher temperature along this path. Yeah. When I heat the gas up, what do I do? When I'm heating the gas, what's happening? Yeah, but what's happening? I'm speeding up all the molecules. I'm increasing the kinetic energy of every molecule. So I'm increasing the average kinetic energy. Okay, how much did I increase the energy of the gas by? Let's say I increased the energy of each molecule by 5 joules, and there were 100 molecules. I increased the total energy by 5,000 joules. Okay? All right. All right. So when I went from here to there along that path, I increased the internal energy by the same amount as if I went from here to there. Is there any difference? So I increase the internal energy by the same amount. What is the difference between this path and that path? I'm sorry?
One's increasing the volume of the gas.
Okay.
Increasing the pressure. One, there's work done.
Exactly. So when I went there, the gas expanded and I did work. I spent money. So I had to earn more. Okay. When I went from here to there, I didn't spend any money. I didn't do any work. All my earnings went into increasing the energy. Did you guys understand that? So along this process, I had to absorb more heat. Okay. So this was the heat absorbed at constant pressure. This was the heat absorbed at constant volume. Okay. So heat absorbed at constant pressure had to be greater than heat absorbed at constant volume to increase the same temperature. Did you guys understand that? All right. Now there's a bit of derivation, but I'm not going to go over the derivation as long as you guys understood that. Okay? All right. Any questions before I move on? You all understand? Yeah. All right, so here's the heat added in going from this temperature to that temperature along constant pressure. Heat added to go along constant volume. Okay? Constant pressure, constant volume. Okay? So this tells you N is the number of moles of gas I have. This is the specific heat at constant volume. This is the specific heat at constant pressure. Okay? So you guys now understand that Cp, specific heat at constant pressure, is greater than specific heat at constant volume. Okay? And it turns out that if the gas is ideal, the difference is equal to R. Okay? So as long as it's an ideal gas, it doesn't matter what the gas is. Okay? All right. So we'll come to that. Okay, this is one derivation I'll show you. So I'll show you how to calculate CV. Okay. CV is you're adding heat to a gas at constant volume. Okay, you're not doing any work. So when you're adding heat, what is happening? You're just speeding up the gas molecules. Okay. Okay, so you're not wasting any energy on work. All the heat is going into changing the internal energy. Okay. So, okay, N is the number of molecules. What does the equipartition of energy say? If you answer this correctly, I'll buy you a soda, but it has to be absolutely correct. No looking at notes.
What's the question one time?
What is the statement of the equipartition of energy? All right, so what this, okay, don't worry about the soda. Okay, so here's a thermodynamic system. So here's a thermodynamic system. I add 1,000 joules of heat to the system. Okay, where is that heat going to? The equipartition of energy says that energy is distributed equally to every degree of freedom. Right. Okay, so each degree of freedom. Did you say that?
No, I thought
No. We were, like when you said it,
Uh-huh.
you just remembered.
Oh, okay. Yeah, I wasn't going to buy you the soda because I didn't hear no answer. So if a system is at temperature T, each degree of freedom is contributing 1/2 kT. Okay, and if each particle has F degrees of freedom, each particle gets that much, F times 1/2 kT. And then if you have total number of N number of particles, that's the total energy in the system. Okay, so that theorem is very important to calculate the energy of the system. Okay, it's very simple calculation. Okay, E equal to N F 1/2 kT. Okay, and you guys go ahead and look at the notes. N times K is equal to N times R. Okay, so this is the number of particles, that's the Boltzmann's constant, that's the number of moles, that's the gas constant. Okay, so the total energy of the system can be written as 1/2 F by 2 nRT. Okay, and CV is related to del E by del T, the internal energy, derivative of internal energy with respect to temperature, which is F over 2 nR. And CV is defined as 1 over N per mole dE by dt. Okay. So this just tells you how much energy increases for every degree rise in temperature. That's all it's telling you. And this is per mole. And so that becomes F over 2R. All right, so what is this? CV equal to F over 2R. Okay. Yeah. So the specific heat at constant volume is the number of degrees of freedom divided by 2 times R. Okay. All right. So for monoatomic gases, F is 3. Okay. For diatomic gases, so here's CV. This is 3 by 2R. For diatomic gases at room temperature, it's 5/2 R. And for more complex molecules, there are higher degrees of freedom and CV is higher. Okay. So this is 3/2 R. This is 5/2 R. And this is F is greater than 5. Okay. All right. Did you guys understand all of that? Okay, I got 5 minutes left. All right, this, again, like I said, I'm not going to show the derivation. This is derived for an ideal gas. Cp minus Cv equal to R. Okay, so Cp is the specific heat, molar specific heat at constant pressure, minus Cv is, and this is equal to R. And this table shows you, so Cp minus Cv, and it shows you for various gases, it's R. See, it's constant. Okay. All right, this ratio is extremely important, and it comes, you encounter it often, so they give it a special symbol, gamma. It's the ratio of specific heats. Okay. And look at this. If you, so remember Cv was F by 2R. Cp is F plus 2 divided by 2R. Okay, so let's see what gamma is. So gamma is Cp by Cv, and it's equal to F plus 2 divided by F. Okay, 1 plus 2 over F. What is F? What is F? What is F? The number of degrees of freedom. Okay, so you see, that tells you the complexity of the molecule. The more complex the molecule, higher the number of degrees of freedom, and smaller this number becomes. Okay, so smaller gamma tells you that the molecules are more complex. Okay, anyway, it's the ratio of specific heat. And so you see gamma, so for more complex molecules, gamma is getting smaller. For monoatomic gases, those are the noble gases, gamma is 1.67. For diatomic gases, there's gamma, 1.4. Okay? All right. So here are the number of degrees of freedom. If you have a monoatomic gas, all it has is 3 degrees of freedom. It can go in this direction, or that direction. Those are the 3 degrees of freedom. Okay? Your diatomic molecule can move in those three directions, but it can also rotate about those 2 axes. So that's 5 degrees of freedom. And polyatomic gases could have more axes of rotation, okay, and so on. So Cv for a diatomic molecule at room temperature, the number of degrees of freedom is 5, so its Cv is 5/2. And gamma for diatomic molecules at room temperature is about 1.4. Okay. So here's the stuff we talked about. This is a graph for hydrogen molecules. Okay, and you see the hydrogen molecule is a diatomic molecule. But at these low temperatures, only 3 degrees of freedom are in play. Cv, which is equal to F by 2R. So at these low temperatures, this is in Kelvin, at up to 100 degree Kelvin, Cv is 3/2 R. For the temperature range from 100 to 1000 degree Kelvin, Cv rises to 5/2 R. Okay. And for temperatures of about 5000 Kelvin, this is in the surface of the sun. For the hydrogen molecule, Cv is 7/2 R. Okay. Higher the Cv, more heat it takes, more heat is needed to raise the temperature. Okay. What is an adiabatic process? What's an adiabatic process? I'm sorry?
Energy remains constant.
No, no.
No energy transfer.
No heat transfer. Okay? So you're not exchanging heat with this environment. Okay, so that's an adiabatic process. Okay, so in an isothermal process, you are absorbing heat. As you're expanding, you're absorbing heat. Okay, so in an adiabatic process, if you expand, okay, so this guy is zero in an adiabatic process. So if the gas expanded, it did work. Where did that energy come from? From the internal energy. Okay, you had no earnings, you spent money, your bank balance went down. Okay, and so internal energy decreased. Remember, this was higher temperature and higher internal energy. Okay, so internal energy decreased. Okay, and what this statement is saying is the following. So this is a very powerful statement. What this is saying is, okay, what is this saying to you guys? What is this equation telling you? I'm sorry? Is it talking to you?
Yes.
All right, what is it telling you? So here is an adiabatic process, and what this is telling you is, okay, you can take any point on the curve. So this is Pi Vi, and Pi Vi to the power gamma is constant. So for on every point on the curve, Pi Vi to the power gamma is constant. That's what it's telling you. Okay, so along an adiabatic so in an adiabatic process, okay, so that's one of the things we like to do in physics. Okay, so here's a process. Along this process, can you say if something is constant? And this guy is constant. Okay. All right. And this is the proof, and again, obviously, I'm not going to go over it. It turns out that along this curve, this guy is constant, but also this is also constant. Okay, so Pi Vi to the power gamma is constant, and Tv to the power gamma minus 1 is constant along those curves. Okay. All right, hang on a second. There's one more thing that I have to tell you before we go. All right, so here is the slab of air. Okay, there's the weight of this air, slab of air. Why isn't this falling down?
This one is pushing it up too.
Okay, so if it's not falling down, there must be a force equal an upward force equal to the weight of this guy. Well, how's the weight coming? Then that means that the pressure at the top is lower than the pressure at the bottom. That's the only way it won't fall down. Okay, so from that fact, now you have concluded that as you go higher, the pressure is decreasing. Okay, and it turns out that if you do the calculation, what you find is the pressure decreases exponentially. Okay, so this is the number of particles, and remember, for an ideal gas, so we are dealing with ideal gases, RT. Okay, so the temperature is constant. So since the pressure is decreasing, the number of molecules is decreasing. Okay, and the pressure decreases because the number of molecules decreases. So this is telling you as you go up, Y is increasing, the number of molecules is decreasing exponentially. Okay. All right, so this is the number density, and here's a very important formula. So this is the number density at ground level minus mgy divided by kT. What is mgy? Does it ring a bell?
The work done by gravity.
I'm sorry?
The work done by gravity.
That's the potential energy of this gas molecule, mgy. Okay, so this is potential energy, and that's the temperature, K times the temperature. Okay, so it seems like the probability of being at that location is proportional to this factor. Okay, and that's the Boltzmann's distribution law. So the probability of an energy level being occupied is proportional to the e to the power minus energy level divided by kT. Okay, so that's an important, very important distribution law. Okay, that you have to know. All right, guys, so I will see